In the winter of 1867, when frost painted delicate patterns across window panes and snow muffled the usual cacophony of city life, the East River performed its annual transformation into something both beautiful and terrifying. A sheet of ice that stretched like frozen silver between two worlds that yearned to touch but remained forever separated. Manhattan and Brooklyn stood as separate cities, gazing at each other across 1,600 feet of water that might as well have been an ocean for all the difficulty it presented to those who needed to cross. The ferry boats that usually plied these waters with rhythmic regularity sat trapped like insects preserved in amber, their paddle wheels frozen mid-revolution, while passengers waited on fog-shrouded docks for ice that might not thaw for weeks. But winter ice was merely inconvenient compared to the river's darker moods. The sudden fog banks that descended without warning, turning familiar waters into landscapes of disorientation, where ferry captains steered by instinct and prayer. The violent currents that could sweep vessels off course, carrying them toward the harbor entrance and the open ocean beyond. The spring floods that turned the East River into a torrent capable of overturning even the sturdiest boats. Year after year, the death toll mounted. Ferry passengers who had kissed their families goodbye that morning never returned home that evening, lost to waters that showed no mercy and offered no second chances. Children learned to fear the river crossing, understanding that fathers who departed for work in the morning might vanish into fog or slip beneath winter ice, becoming just another name in the newspaper's grim accounting of lives claimed by the treacherous channel. By 1869, as America struggled to heal wounds left by civil war and rebuild a nation torn apart by conflict, two great cities continued their awkward separation. Manhattan growing upward, with buildings that challenged the sky, Brooklyn spreading outward with neighborhoods that housed nearly 500,000 souls. The economic absurdity of this division grew more apparent each year, as goods and workers required hours to travel distances that could be walked in minutes if only some permanent connection could span the impossible gap. Engineers had proposed bridges before, timber structures that would rot within decades, stone arches that would require so many river supports they would block ship traffic and create artificial dams during ice seasons. Every conventional solution created problems worse than those it attempted to solve, leaving the two cities to continue their frustrated courtship across waters that refused to be conquered by ordinary means. Then, a German immigrant named John Augustus Roebling, who had already proven his genius by building suspension bridges across lesser rivers, gazed upon the East River and saw not obstacles, but opportunities. Where others saw impossible width, he envisioned steel cables, strong enough to span distances that would have been unthinkable just decades earlier. Where conventional engineers saw the necessity of river supports that would interfere with shipping, he imagined towers so tall they would allow full-rigged sailing ships to pass beneath without lowering their masts. His vision called for something that had never been attempted at such scale: the world's longest suspension bridge, using revolutionary steel cables instead of the iron chains that had served previous designs. A structure so ambitious that critics called it Roebling's folly, predicting it would either never be completed or collapse catastrophically when subjected to the weight of traffic and the forces of nature. Yet Roebling possessed something more valuable than conventional wisdom. He understood that civilization advances not through timid acceptance of limitations, but through audacious challenges to everything previously considered impossible. His bridge would use steel, that miraculous material that combined the strength of iron with resilience that could bend without breaking. His design would incorporate safety factors so generous that the structure could support loads far exceeding anything it would ever encounter during normal operation. In June 1869, as Roebling conducted final surveys for his masterpiece, a ferry accident during docking crushed his foot against a piling, seemingly a minor injury that would heal within weeks. But infection set in. Tetanus, that invisible killer that medical science understood but could not cure. Within a month, John Roebling was dead. His impossible dream left to a son who had learned engineering at his father's side, but now faced the challenge of completing a project that critics had called impossible, even when the master himself proposed it. Tonight, we follow the 14-year journey of that impossible dream, from the underwater chambers where men worked in conditions that would kill them with mysterious illness, to the heights where steel cables were spun thread by thread across empty sky, to the final triumph when two cities became one through the patient determination of those who refused to accept that any challenge could remain permanently unconquerable. This is the story of how vision became reality. One stone block, one steel wire, one impossible day at a time. Welcome to the Sleepy Structures, where the greatest achievements in human engineering become gentle bedtime stories, and the most impossible construction projects unfold their secrets in whispers, soft as evening wind across calm water. I'm here to guide you through the remarkable tales of builders who refuse to accept limitations, engineers who transform vision into reality using nothing but determination, mathematics, and the unshakable belief that human ingenuity could overcome any obstacle that nature or circumstance placed in their path. Tonight, we journey to the shores of the East River in the decades following America's Civil War, to explore how 19th century engineers accomplished what seemed impossible, even by today's standards. How did they build foundations in underwater darkness, where pressure could crush human lungs, and mysterious illness could paralyze workers within hours? How did they spin steel cables across distances that no structure had ever bridged? How did they create something so beautiful it became a symbol not just of engineering triumph, but of the very idea of connection itself? These are the questions that will carry you gently into sleep as we explore the construction techniques, the human determination, and the sheer audacity that created the Brooklyn Bridge. The steel and stone monument that proved two separated cities could become one unified metropolis through the patient application of engineering principles that pushed every limit of 19th century technology. Rest comfortably. Let your mind drift to foggy harbors where sailing ships passed beneath rising towers, to workshops where steel wire was drawn to specifications that demanded perfection, to construction sites where workers solved problems that had never been encountered before. As we begin our peaceful exploration of how the impossible became inevitable when necessity met unwavering vision. The story of the Brooklyn Bridge begins now. In the decades following America's Civil War, as the nation attempted to heal divisions that had torn families apart and redraw maps that had been rewritten in blood, two great cities stood on opposite shores of the East River, so close that voices could sometimes carry across the water on quiet mornings, yet so impossibly separated they might as well have existed on different continents. Manhattan, that narrow island of rock and ambition, had transformed itself from colonial trading post into the commercial heart of a reunited nation. Buildings rose higher each year, challenging gravity with iron frameworks and architectural audacity that suggested no limit existed to vertical growth. Banks, businesses, and burgeoning industries crowded together in streets where property values climbed as relentlessly as the structures themselves, creating an urban density that seemed destined to continue forever. Yet Manhattan possessed a fundamental limitation that no amount of construction ingenuity could overcome. It was an island, surrounded by water that separated it from the farmlands, residential neighborhoods, and industrial facilities that a growing metropolis required for sustainable expansion. The island's geography, that had once protected colonial settlers now confined their descendants within boundaries that grew more restrictive with each passing year. Brooklyn, by contrast, sprawled across Long Island's western shore with the comfortable confidence of a city that possessed unlimited room for growth. Nearly 500,000 residents called Brooklyn home by the late 1860s, making it America's third largest city, despite lacking the concentrated commercial development that characterized Manhattan's crowded streets. Neighborhoods expanded steadily eastward, absorbing farmland and forest into residential districts that housed families seeking the space and comfort that Manhattan could no longer provide. The economic relationship between these two cities created absurd inefficiencies that grew more pronounced as both populations expanded. Workers who lived in Brooklyn's affordable housing districts might spend hours each day simply attempting to reach their Manhattan employment, while Manhattan businesses struggled to import the goods and materials they required from Brooklyn's warehouses and manufacturing facilities. The East River that separated these urban centers was neither east nor truly a river in the conventional sense. This tidal strait connecting Long Island Sound with New York Harbor flowed both directions depending on oceanic tides, creating currents so complex and unpredictable that even experienced ship captains approached the passage with cautious respect. During flood tides, water rushed through the strait at velocities exceeding 4 miles per hour, while ebb tides reversed the flow with equally powerful force. Winter transformed the East River from merely difficult to genuinely deadly. Ice formed during cold snaps, creating hazards that range from annoying to catastrophic, depending on temperature and duration. Thin ice sheets could damage ferry paddle wheels, forcing captains to navigate carefully through channels that required constant adjustment as ice conditions changed throughout each day. Thick ice could halt ferry service entirely for days or weeks, stranding passengers and paralyzing commerce between the two cities. The ferry system that attempted to bridge this aquatic divide had evolved into a complex network of competing companies, operating dozens of boats on routes connecting various Manhattan and Brooklyn landing points. During fair weather, these ferries provided reasonably reliable service, with departures occurring every few minutes during peak travel hours. But reliability crumbled whenever weather conditions deteriorated beyond the merely inconvenient. Fog presented perhaps the most treacherous challenge to ferry operations, descending without warning and reducing visibility to distances measured in feet, rather than the hundreds of yards that safe navigation required. Captains navigating by compass and intuition sometimes collided with other vessels, or missed their landing points entirely, forcing passengers to endure extended journeys through gray uncertainty, while hoping their captain's skill would eventually deliver them to their intended destination. The human cost of this aquatic separation mounted steadily as both cities' populations grew. Newspaper accounts from the 1860s documented a grim toll of lives lost to ferry accidents, drownings, and the various disasters that occurred when humans attempted to cross water that refused to be tamed by conventional transportation methods. Families learned to treat each river crossing with the same careful concern they might apply to much longer and more obviously dangerous journeys. The economic cost proved equally significant, though measured in lost productivity rather than lost lives. Businesses faced unpredictable delays in receiving materials and supplies from across the river, while workers arrived late or not at all when weather disrupted ferry schedules. The inefficiency of requiring water transport for every crossing between the two cities created artificial barriers to commerce that limited growth and opportunity for residents of both communities. Bridge proposals had surfaced periodically throughout the decades, each one dismissed as impractical, for reasons that seemed insurmountable given available technology and engineering knowledge. Conventional stone arch bridges would require so many supporting pillars in the river that ship traffic would be severely restricted, while the approaches would need to rise so high that connecting them to city streets would require extensive ramps, occupying valuable urban real estate. Timber bridges face the inevitable problem of rot and fire, making them unsuitable for permanent construction expected to last generations. Iron truss bridges, while structurally sound for shorter spans, could not extend across 1,600 feet of water without intermediate supports that would create the same shipping obstacles as stone arches. Every conventional bridge design proved inadequate when confronted with the specific challenges presented by the East River's width, depth, and importance to maritime commerce. Tunnel proposals fared no better, as excavation technology of the 1860s could not reliably create underwater passages through the complex geology beneath the East River. The risk of catastrophic flooding during construction, combined with the difficulty of ventilating such a long tunnel for pedestrian and vehicle traffic, made underground connections equally impractical despite their theoretical appeal. Suspension bridges offered the only viable solution to spanning such distances without intermediate river supports. But no suspension bridge of sufficient length had ever been successfully constructed. The longest existing suspension span measured less than 1,000 feet, leaving a significant gap between proven capability and the requirements for bridging the East River. Engineers who proposed suspension solutions faced legitimate skepticism from observers who questioned whether scaling up existing designs by nearly double would encounter unknown problems that might prove insurmountable. John Augustus Roebling possessed unique qualifications for addressing this skepticism, having already built successful suspension bridges across the Allegheny River at Pittsburgh and the Niagara River between the United States and Canada. These earlier projects had proven his ability to design suspension spans that could carry not just pedestrian traffic, but the enormous loads imposed by railroad trains, crossing at speeds and weights that subjected bridge structures to dynamic forces, far exceeding those from stationary loads. His proposal for the East River crossing incorporated innovations that addressed every concern raised by critics of suspension bridge technology. Steel cables would replace the iron chains used in earlier designs, providing superior strength and reliability, while reducing the weight that towers would need to support. Gothic stone towers of unprecedented height would rise 276 feet above the water, allowing full-rigged sailing ships to pass beneath without lowering their mass, while creating the elevation necessary for cable catenary curves that would support the suspended roadway. The bridge would be over-engineered with safety factors so generous that it could theoretically support 6 times the maximum load it would ever encounter during normal operation. This redundancy addressed fears that unforeseen forces might cause catastrophic failure, providing margins of safety that seemed almost excessive, but reflected Roebling's understanding that public confidence required proof of indestructible permanence. Yet even as plans reached final form and political support coalesced behind the project, fate delivered a cruel blow that would test whether vision could survive the loss of the visionary who conceived it. But with plans approved and political will finally aligned behind this audacious vision, the project faced its first terrible tragedy, even before construction could begin. And the impossible dream threatened to die with the dreamer who had conceived it. In June 1869, as final surveys were being conducted to establish precise tower locations, John Roebling stood on a Brooklyn ferry slip, measuring angles and calculating positions with the meticulous attention to detail that had characterized his entire engineering career. A ferry approaching the dock struck the piling where Roebling stood, crushing his right foot between timber and boat in an accident that seemed minor, a workplace injury that would heal within weeks and leave nothing worse than painful memories. But tetanus bacteria entered through the wound, invisible killers that 19th century medicine understood but could not combat. Within days, the great engineer developed the characteristic symptoms: muscle stiffness, difficulty swallowing, the terrible spasms that gave the disease its common name of lockjaw. Despite the desperate efforts of doctors who tried every treatment known to medical science, John Roebling died on July 22, 1869, just 3 weeks after the accident that had seemed so survivable. His son Washington Augustus Roebling, 32 years old and recently returned from service as a Union Army engineer during the Civil War, inherited not just his father's plans, but the terrible burden of completing a project that critics had called impossible, even when the master himself proposed it. The bridge company trustees, recognizing that Washington had worked closely with his father and understood every aspect of the design, appointed him chief engineer, despite his relative youth, and the enormous challenges that lay ahead. Construction officially commenced in January 1870, as workers began the most dangerous and technically challenging phase of the entire project, building foundations for towers that would rise higher than any structure yet erected in New York, foundations that would need to reach solid bedrock beneath the East River's muddy bottom, while supporting loads that would test the limits of stone masonry and engineering calculation. The solution to this foundation challenge lay in a technology that seemed almost magical to observers, unfamiliar with its principles: pneumatic caissons, massive wooden chambers that would be floated into position, then gradually sunk to the riverbed, while workers excavated material from inside pressurized compartments that kept water from flooding the workspace. These caissons would serve simultaneously as construction platforms during the descent and as permanent foundation elements once they reached bedrock and were filled with concrete. The Brooklyn caisson, constructed first to refine techniques before attempting the more difficult Manhattan foundation, measured an almost unbelievable 168 feet long by 102 feet wide. Larger than most buildings in New York, yet designed to be gradually lowered through 60 feet of water and then excavated downward through mud, sand, and rock until it reached the solid foundation necessary for supporting a tower weighing thousands of tons. Construction of this massive wooden box required timber engineering that pushed carpentry skills to their limits. Yellow pine logs from southern forests were assembled into walls 9 feet thick at the base, creating structures strong enough to withstand both the water pressure from outside and the air pressure that would be maintained inside during the excavation process. Iron reinforcement bands wrapped around the structure like giant barrel hoops, holding everything together against forces that could tear lesser construction apart. The top of the caisson remained open to the air during the initial float and positioning, but the bottom featured an enclosed chamber that would eventually house the workers who would dig the foundation. This working chamber, 9 feet tall and extending across the entire caisson footprint, would become both workplace and prison for men who descended into conditions unlike anything encountered in conventional construction. Once the caisson was floated into position above the designated tower location in early March 1870, the real work began. Workers inside the sealed chamber began excavating riverbed material, while compressed air pumped into the space prevented water from flooding through the open bottom. As material was removed, the massive structure gradually sank under its own weight, plus the additional weight of masonry that was being added to the top, creating the permanent tower that would eventually rise high above the water. Entering the caisson working chamber required passing through an airlock, a small chamber where pressure could be gradually increased to match the conditions in the working space below. Workers climbed down ladders in the airlock shaft, feeling their ears pop as atmospheric pressure increased with each descending level. Entering a world of compressed air, where even breathing felt different as their lungs adapted to conditions no human had evolved to handle. Inside the working chamber, conditions challenged every aspect of human endurance. The only illumination came from candles and oil lamps whose flames burned with strange colors in the oxygen-rich compressed air. The constant noise of excavation tools striking rock, combined with the hiss of air pumps and the groaning of timber under enormous pressure, created a cacophony that prevented normal conversation and forced workers to communicate through hand signals and shouted commands. The excavation work itself required removing everything between the caisson's current position and the bedrock that lay somewhere below. River mud that behaved like liquid when disturbed, sand that flowed like water through any opening, clay that had to be cut into chunks small enough to be hauled away, and occasional boulders that required blasting with explosives in the confined space, where any miscalculation could prove catastrophic. Material removed from the working chamber was loaded into buckets and hauled up through shafts to the surface, where it was dumped into scows for disposal elsewhere in the harbor. The pace of excavation determined how quickly the caisson would descend, with each foot of progress requiring the removal of tons of material, while constantly fighting against mud and water that sought every opportunity to flood into the artificial bubble of compressed air. As the Brooklyn caisson descended deeper through the spring and summer of 1870, workers began experiencing strange symptoms that had no obvious cause. Some men reported feeling dizzy or weak after emerging from their shifts, while others developed joint pain that seemed unrelated to the physical demands of their work. A few workers collapsed with mysterious paralysis that doctors couldn't explain, their legs refusing to function despite showing no obvious injury or disease. Washington Roebling, who descended regularly into the caisson to inspect progress and consult with foremen about excavation challenges, experienced these symptoms himself, but initially dismissed them as temporary fatigue that would pass with rest. Medical understanding of decompression sickness would not develop for several more years, leaving workers and supervisors alike to puzzle over an illness that seemed to strike randomly and without clear cause. By September 1870, the Brooklyn caisson had reached 44 feet below the river's surface, encountering bedrock that engineers deemed suitable for supporting the tower's enormous weight. Workers began the process of filling the working chamber with concrete, transforming the excavation space into solid foundation, while ending the dangerous phase of pressurized underground work that had already claimed several lives and injured dozens more. The Manhattan caisson, begun in May 1871, would prove even more challenging than its Brooklyn predecessor. The deeper water and more difficult geology on the Manhattan side meant workers would need to descend even further into compressed air conditions that increased the mysterious illness to epidemic proportions. Washington Roebling would descend into these depths repeatedly to assess progress and consult with workers, subjecting himself to the same dangerous conditions that were destroying the health of men under his command. By the time the Manhattan caisson reached 78 feet below the surface in May 1872, the death toll and injury count had mounted to levels that shocked even hardened construction veterans. Yet the foundations were finally complete, resting on bedrock that would support towers destined to become the most recognizable landmarks on the New York skyline, built at a human cost that no one had fully anticipated when construction began. With the foundations finally resting on solid bedrock beneath the East River's muddy bottom, the bridge project transformed from underground excavation into a visible construction challenge that would require materials on a scale unlike anything previously attempted in American engineering. Materials that would need to be gathered from quarries, forests, and foundries scattered across thousands of miles, then transported to a single construction site where quality and timing would determine success or failure. The sheer volume of materials required for completing the bridge challenged comprehension even among experienced construction professionals. The two towers alone would consume over 60,000 cubic yards of granite and limestone, representing millions of individual stone blocks that would need to be quarried, shaped, transported, and assembled with precision, measured in fractions of inches, despite weighing up to 6 tons each. Granite, That igneous stone formed deep within the earth and cooled over millions of years into crystalline perfection, would provide the primary building material for tower exteriors that needed to withstand not just the bridge's structural loads, but centuries of weathering, from salt air, temperature extremes, and the general abuse that urban environments inflicted on even the most durable materials. The search for suitable granite sources led engineers to the coast of Maine, where island quarries had been supplying building stone to American cities since colonial times. Vinalhaven Island and nearby Hurricane Island, located in Penobscot Bay off Maine's rocky coastline, possessed granite deposits of exceptional quality, fine-grained stone with consistent color and texture that could be quarried in large blocks without the natural flaws and fractures that compromise lesser deposits. But these remote island locations, while geologically ideal, created transportation challenges that required careful coordination of quarrying schedules with shipping availability and construction needs. The quarrying process itself represented a delicate balance between productivity and quality control. Workers used hand drills and black powder charges to split massive blocks from the living rock, creating rough shapes that would be refined through successive stages of cutting and dressing before reaching the precision required for tower masonry. Each block began its journey as part of an ancient mountain, transformed through human labor into geometric perfection that would serve civilization for centuries to come. Transportation from Maine quarries to the Brooklyn construction site required coordination between multiple shipping companies and careful timing to ensure materials arrived when needed, without creating storage problems at the constrained urban work site. Granite blocks were loaded onto coastal schooners and barges that sailed south along the Atlantic seaboard, a journey of several hundred miles that could take days or weeks, depending on weather conditions, and sea states that ranged from glassy calm to life-threatening storm. The arrival of each stone shipment triggered carefully choreographed unloading operations at the construction site, where steam-powered derricks lifted multi-ton blocks from ship holds and positioned them in temporary storage areas, where masons would perform final shaping before installation. Any damage during transport required the entire process to begin again, with replacement blocks ordered from Maine quarries, and weeks or months passing before substitute materials could arrive. Limestone for mortar and interior construction came from deposits closer to New York, particularly the famous Rosendale cement quarries in Ulster County along the Hudson River Valley. These limestone formations, formed from ancient seabeds and compressed over geological ages, produced a natural hydraulic cement that would set underwater, an essential property for bridge construction, where masonry would be exposed to constant moisture from rain, river spray, and the humid air that characterized New York's maritime climate. The Rosendale quarries operated year-round to meet the bridge's enormous appetite for cement, with workers mining limestone through the winter months when construction activity slowed, and stockpiling processed cement for the busy spring and summer building seasons. The limestone was crushed, heated in massive kilns to drive off water and carbon dioxide, then ground into the fine powder that would be mixed with sand and water to create the mortar binding individual stones into unified masonry structures. Steel wire for the suspension cables represented perhaps the most critical material challenge, as no margin for error existed in cable construction, where even microscopic flaws could propagate into catastrophic failures under the enormous loads the bridge would impose. The Roebling family had established their own wire mill in Trenton, New Jersey, specifically to produce the specialized wire rope and bridge cable required for John Roebling's suspension bridge designs, ensuring quality control that outside suppliers might not maintain. The steel itself came from foundries in Pennsylvania, where coal-fired furnaces transformed iron ore and carbon into the alloy that combined strength with flexibility. Steel that could bend without breaking, absorb dynamic loads from traffic and wind, and maintain its properties through temperature extremes, ranging from summer heat that could soften lesser materials to winter cold that made brittle metals shatter under sudden stress. Drawing wire to the precise specifications required for bridge cables demanded specialized equipment and extraordinary skill from workers who understood that imperfections invisible to the naked eye could compromise cable integrity. Each wire had to meet exact diameter specifications across its entire length, possess uniform tensile strength, verified through testing procedures that destroyed sample sections, and show no surface flaws or internal inclusions that might serve as crack initiation points under the cyclical loading that bridge service would impose. The total wire requirement approached a figure that seemed almost absurd. Over 14,000 miles of individual wire would be needed to complete the 4 main cables, enough to stretch more than halfway around the Earth at the equator. This wire would be manufactured over a period of several years, with production carefully scheduled to deliver materials as cable spinning operations progressed, and storage limitations at the construction site prevented accumulation of large stockpiles. Yellow pine timber from southern forests provided material for the roadway deck and various temporary structures needed during construction. These massive logs, harvested from virgin forests that had been growing since before European colonization, possessed strength and durability that modern plantation-grown lumber could not match. The logs were floated down rivers to coastal ports, loaded onto ships, and delivered to New York, where sawmills would cut them into the precise dimensions required for roadway planking. Iron and steel components for the roadway support trusses, suspender cables, and countless other structural elements came from foundries and fabrication shops scattered across Pennsylvania and New Jersey. Each piece was individually designed and manufactured to exact specifications with no interchangeable parts or standard components that might simplify the construction process. Drawings showed precise dimensions and connection details, while full-scale templates verified that fabricated pieces would fit properly when assembled at the construction site. Quality control for all materials required constant vigilance from inspectors, who understood that accepting substandard materials could compromise the entire project. Stone blocks were examined for cracks, inclusions, and proper dimensions before acceptance. Wire samples underwent destructive testing to verify tensile strength and uniformity. Timber was inspected for rot, knots, and grain orientation that might affect structural performance. Iron and steel components received dimensional checks and metallurgical analysis to confirm they met specifications. The logistics of coordinating material deliveries from dozens of suppliers, located hundreds or thousands of miles from the construction site, required administrative capabilities that rivaled the engineering challenges of actually building the bridge. Shipping schedules had to account for weather delays, seasonal variations in quarry and mill operations, and the constantly changing construction timeline that determined when specific materials would be needed at the work site. Storage and protection of materials at the construction site created additional challenges in the dense urban environment, where available space commanded premium prices, and temporary storage facilities had to protect valuable materials from weather, theft, and accidental damage. Granite blocks filled vacant lots near the bridge approaches, while steel components occupied warehouses rented specifically for bridge construction purposes. By the time tower construction began in earnest during 1872, the material supply systems were functioning with remarkable efficiency, despite the complexity of gathering resources from across America and coordinating their delivery to a single point where thousands of workers would transform raw materials into architectural achievement that would define the New York skyline for generations to come. With mountains of granite arriving steadily from Maine, quarries and foundations firmly anchored to bedrock beneath the river's muddy bottom, the bridge transformed from invisible underground work into a spectacle that would captivate New York's residents for the next 4 years. two Gothic towers rising stone by stone toward heights that would make them the tallest structures in the Western Hemisphere, challenging the sky itself with architectural ambition that seemed to defy gravity and common sense in equal measure. The construction of each tower began in 1872, as the first courses of granite were laid upon the massive caisson foundations that had cost so much human suffering to position correctly. These initial courses would bear the weight of everything built above them, transferring loads measured in thousands of tons down through the caisson structure into bedrock that had supported nothing heavier than river mud for millions of years. The granite blocks that would form these towers arrived at the construction site as rough shapes that approximated their final dimensions. But achieving the precision required for permanent masonry demanded additional work by skilled stonecutters, who transformed quarry blocks into geometric perfection. Each face that would contact adjacent stones needed to be dressed smooth and flat, creating surfaces so perfectly mated that mortar served primarily to fill microscopic irregularities, rather than to compensate for poor stone cutting. The tools available to these craftsmen had changed little since medieval cathedral builders developed techniques for shaping stone with hand tools and patient labor. Steel chisels driven by hammers removed material gradually, while abrasive stones smoothed surfaces to tolerances that modern machinery would struggle to improve upon. The work required both physical strength and artistic sensitivity, as masons learned to read the grain patterns in granite and understand how each stone would respond to chisel strikes. Quality control during stone preparation occupied the attention of dedicated inspectors who used straight edges, squares, and measuring instruments to verify that each block met specifications before approval for installation. Stones that failed inspection were either reworked if defects could be corrected, or rejected entirely and sent back to the quarries for replacement. This uncompromising approach to quality ensured that only perfection would be built into structures expected to stand for centuries. The mortar binding these carefully prepared stones used Rosendale hydraulic cement mixed with sand and water, according to formulas that had been refined through years of experimentation. The mixture needed to be workable enough for masons to spread it evenly across stone surfaces, yet strong enough when cured to bond granite blocks into unified structures capable of resisting forces that would destroy lesser construction. Setting each stone required coordination between multiple workers, using techniques that dated back to ancient Egypt and Rome. Wooden cranes powered by steam engines lifted multi-ton blocks from ground-level storage areas, while riggers guided suspended stones into position, using rope systems that allowed precise adjustments measured in fractions of inches. The final placement demanded judgment that only experienced masons could provide, as stones needed to be positioned exactly right before mortar began setting and corrections became impossible. The towers rose through the spring and summer of 1872 at rates that varied with weather conditions and material availability, averaging perhaps one course every few days, as thousands of individual stones were lifted, positioned, and bonded into permanent masonry. Each course added several feet to the growing structures, transforming the construction site from ground-level activity into increasingly vertical work that required workers to climb higher each day to reach their workstations. Scaffolding systems built around the rising towers provided platforms where masons could work, while also supporting the lifting equipment necessary for raising stones to ever-increasing heights. These wooden frameworks represented significant engineering achievements in themselves, as they needed to support enormous loads while remaining stable, despite wind forces that increased dramatically with height above the river's surface. The design of the towers incorporated Gothic Revival architectural elements that served both aesthetic and structural purposes. Pointed arches spanning 117 feet across each tower's width would eventually allow sailing ships to pass beneath the completed bridge, with their masts fully rigged, while also creating shapes that distributed loads more efficiently than rectangular openings would have managed. The Gothic style, popular in American architecture during the 1870s, gave the towers a timeless quality that suggested medieval cathedrals adapted for industrial age purposes. As the towers climbed higher through 1873 and 1874, they became landmarks visible from miles away, stone monuments to human ambition that announced the bridge project's progress to anyone who cared to look toward the East River. Newspapers published regular updates on tower heights, while artists created illustrations showing the partially completed structures rising from their riverside foundations like abstract sculptures that would eventually support the steel cables stretching between them. Working conditions for the masons and laborers building these towers grew more challenging as heights increased and exposure to weather became more severe. Wind that barely registered at ground level could become fierce gales at elevations approaching 200 feet, making it dangerous to work on days when gusts might blow workers off exposed platforms or overturn suspended stone blocks into deadly projectiles. Rain turned work surfaces slippery and made mortar unworkable, while winter freezing prevented masonry work entirely during the coldest months. The Brooklyn Tower reached its full height of 276 feet, above mean high water in May 1875, representing 3 years of nearly continuous construction and the labor of hundreds of workers who had climbed those growing stone stairways daily to add their contribution to this rising monument. The Manhattan Tower followed 1 year later in May 1876, completing the pair of Gothic stone pillars that would support the steel cables still waiting to be strung across the river's width. The precision achieved during tower construction exceeded specifications that had seemed impossibly demanding when the project began. The two towers stood exactly vertical when measured with plumb lines that hung from their summits, while the spacing between them measured precisely 595.5 feet. Accuracy achieved through survey techniques that required constant adjustment for temperature changes, earth tides, and the countless small movements that affected measurements across such distances. Interior spaces within the towers housed the machinery and anchor points that would eventually support the suspension cables, with vaulted chambers created during construction by leaving specific areas hollow while building solid masonry around them. These interior spaces, invisible from outside but essential for bridge function, demonstrated the three-dimensional thinking required to create structures that served both architectural and engineering purposes. The completion of both towers marked a psychological turning point in the bridge project, as skeptics who had predicted the structure would never be built now faced undeniable evidence that Washington Roebling and his team were accomplishing exactly what John Roebling had envisioned. The towers stood as proof that stone masonry could rise to heights previously reserved for wooden structures and steel frameworks, creating permanent monuments that would outlast any conceivable bridge deck or cable system that might eventually require replacement. Yet these magnificent towers represented only the beginning of the construction challenge, as the most technically demanding phase still lay ahead. Stringing steel cables across the 1,600-foot gap between towers, creating the suspended structure that would transform separate stone pillars into a unified bridge capable of carrying the commerce and humanity that would flow between two cities destined to become one. With the Gothic towers standing complete against the New York skyline, like stone sentinels waiting for their purpose to be fulfilled, the bridge project entered its most technically demanding phase, the construction of steel cables that would span the impossible distance between towers, while supporting loads that no suspension bridge had ever been designed to carry, creating aerial highways of woven wire that would challenge every assumption about what materials could accomplish when engineered to perfection. The moment of truth arrived on a clear day in June 1876, when the first individual wire was successfully carried across the river from the Brooklyn anchorage, over the Brooklyn Tower, across the open span to the Manhattan Tower, and down to the Manhattan anchorage. A journey of nearly 3,600 feet that this thin steel thread would repeat thousands of times as workers gradually built the massive cables that would transform separated towers into a unified suspension system. This inaugural wire crossing required careful preparation and coordination as workers positioned traveling wheels on temporary support cables that had been strung between the towers specifically to carry the wire-spinning equipment. The traveling wheel, essentially a grooved pulley system that could roll along the temporary support cable while carrying the steel wire, represented one of several innovations that Washington Roebling and his team developed specifically for this unprecedented construction challenge. The wire itself came from the Roebling family's Trenton mill on large wooden spools, each containing approximately 3,000 feet of steel, drawn to precise specifications that demanded uniformity across every inch of length. The wire diameter measured exactly 0.192 inches, thick enough to possess adequate strength, yet thin enough to be flexible and relatively easy to handle during the spinning process that would continue for the next 2 years. The spinning process followed a methodical sequence that would be repeated over 19,000 times for each of the 4 main cables. A loop of wire was carried across the river by the traveling wheel, creating 2 parallel strands running from anchorage to anchorage. These wires were positioned precisely according to patterns that would build up circular cable cross-sections strand by strand, with each new wire placed adjacent to its predecessors in carefully calculated positions. Workers stationed on platforms built along the tower tops and at mid-span locations guided each wire into its proper position, using hand tools to adjust placement before the wire was secured temporarily with binding wire that would hold it in place until the entire strand was complete. This positioning work required extraordinary attention to detail, as errors in wire placement would propagate through subsequent layers and potentially compromise the geometric perfection necessary for optimal cable performance. The weather played an enormous role in determining when cable spinning operations could proceed, as wind affected the traveling wheel's stability and made it dangerous for workers to operate on exposed platforms hundreds of feet above the water. Strong winds could set wires swinging in complex patterns that made precise positioning impossible, while rain made surfaces slippery and reduced visibility that workers needed for coordinating their activities across the long distances separating workstations. Temperature variations created additional challenges, as steel wire expanded and contracted with temperature changes in ways that affected cable tension and geometry. Workers learned to account for these thermal effects, adjusting wire tensions throughout each day as temperatures rose and fell, ensuring that the final cable dimensions would be correct when measured under standard temperature conditions. Each of the 4 main cables would ultimately contain 5,434 individual wires, organized into 19 separate strands, with each strand containing 286 wires arranged in specific geometric patterns that distributed loads evenly throughout the cable cross-section. This organizational scheme allowed cables to be built up systematically, while maintaining the structural integrity necessary for supporting the bridge deck that would eventually be suspended from them. The strand-by-strand construction process meant that cable spinning proceeded through distinct phases, with workers completing one entire strand before beginning the next. This approach simplified quality control and allowed systematic inspection of each completed strand before additional wires were added. Once all 19 strands were complete, the entire cable would be compacted using specialized equipment that squeezed the individual wires together, transforming the cable from a loosely bundled collection of wires into a tightly compacted cylinder. This compacting process, performed using hydraulic jacks and specially designed clamps that work their way along the cable length, reduce the cable diameter while increasing the density of the wire packing. The final compacted diameter measured 15.75 inches, large enough to dwarf any cable previously used in suspension bridge construction, yet small enough to be aesthetically pleasing and aerodynamically efficient. Wire wrapping provided the final step in cable construction, as workers wound additional wire around the outside of the compacted cable, creating a protective layer that would shield the structural wires from weather and corrosion. This wrapping wire was applied under tension, creating a tight spiral that squeezed the cable even more, while providing a smooth exterior surface that would shed water and resist the accumulation of debris. The completed cables possessed strength that exceeded the bridge's structural requirements by generous safety margins, capable of supporting loads 6 times greater than anything the bridge would encounter during normal service. This over-engineering reflected Washington Roebling's determination to create a structure so robust that no conceivable accident or overload could threaten its integrity, providing public confidence that would be essential for acceptance of suspension bridge technology on such an unprecedented scale. The cable anchorages that secured these massive steel ropes to solid ground represented engineering achievements comparable to the cables themselves. Each anchorage consisted of enormous masonry structures measuring 129 feet long by 119 feet wide, extending deep into bedrock, where massive iron anchor plates and bars transferred cable loads into the earth. The anchor bars, forged from iron and embedded in masonry that filled excavated chambers, created mechanical connections between steel cables and stone foundations that would resist the enormous pulling forces generated by the suspended bridge deck. Inside the anchorage structures, the 4 main cables divided into individual strands that spread out like roots of a great tree, each strand connecting to separate anchor bars that distributed loads across the entire anchorage footprint. This fan-shaped distribution prevented stress concentrations that might damage the anchorage masonry, while ensuring that even if some anchor bars failed, the remaining connections would maintain cable security. Construction of the anchorages had proceeded simultaneously with tower construction, as workers excavated deep chambers in bedrock, installed anchor bars and plates, then filled the excavations with masonry that bonded everything into unified structures capable of resisting forces that could rip lesser construction from the earth. The interior chambers remained accessible through tunnels, allowing future inspections of the anchor connections that would hold the bridge in place for centuries. By the summer of 1878, all 4 main cables had been completed, compacted, and wrapped, hanging in graceful catenary curves between towers and stretching away to the anchorages like steel rainbows that caught sunlight and gleamed against the sky. These cables represented the most visible symbol of the bridge project's technical achievement, proof that human engineering could create structures of unprecedented scale, using materials pushed to the limits of their capabilities. The cables also represented a transition point in the construction sequence, as the most technically challenging work was finally complete, and the project could move forward to the more conventional construction tasks of building the roadway that would be suspended from these steel arteries. Yet even as workers prepared for this next phase, they understood that the cables themselves were more than structural elements. They were monuments to the wire drawers in Trenton, the workers who had risked their lives spinning wire across empty sky, and the engineering vision that had proven steel could be woven into strength sufficient for bridging rivers and connecting cities. But these magnificent steel cables, hanging in graceful curves that seemed to defy the very laws of nature, would be nothing more than beautiful sculptures without the massive stone anchors that held them to the earth. Structures so large and so deeply rooted in bedrock that they represented entire buildings, hidden mostly underground, existing solely to resist forces that could pull mountains from their foundations if not properly contained. The anchorages that secured the Brooklyn Bridge's suspension cables to solid ground represented engineering challenges that rivaled the more visible aspects of bridge construction, requiring excavations that descended deep into Manhattan and Brooklyn bedrock, while creating masonry structures massive enough to resist the pulling forces generated by cables supporting thousands of tons of suspended roadway and traffic. Each of the 4 anchorages, 2 on the Brooklyn shore and 2 on the Manhattan side, measured 129 feet in length by 119 feet in width at their base, occupying footprints larger than most commercial buildings in New York. Yet these surface dimensions revealed only a fraction of the structure's true scale, as the anchorages extended downward through dozens of feet of soil and rock to reach the solid bedrock that would provide ultimate resistance to cable pull. Construction of the anchorages had begun in 1873, proceeding simultaneously with tower construction, as workers excavated enormous chambers into the earth, removing hundreds of thousands of cubic yards of material to create the underground spaces where anchor bars and plates would be installed before being buried forever beneath masonry that would transform excavated caverns into solid resistance against forces that could measure in millions of pounds. The anchor bars themselves represented marvels of 19th century metallurgy, forged from wrought iron in sizes and configurations that pushed the capabilities of available foundries and fabrication facilities. Each bar measured several inches in diameter and extended for dozens of feet through the anchorage structure, with one end connected to anchor plates that would receive the divided cable strands, and the other end embedded in masonry and bedrock that would prevent any possible movement under load. The anchor plates, massive iron castings that resembled oversized arrowheads or spear points, provided the connection interface between the flexible steel cables and the rigid iron anchor bars. Each plate featured multiple holes through which individual cable strands would be threaded and secured, distributing the cable's total load across numerous connection points, rather than concentrating forces at single locations, where metal fatigue might eventually create failures. Installing these anchor systems required precision that challenged the available survey and alignment tools, as each anchor bar needed to be positioned exactly according to plans that specified 3-dimensional locations with tolerances measured in fractions of inches. The bars had to align perfectly with the cable geometry that would be established years later when cable spinning was complete, requiring workers to set positions based on calculations and predictions, rather than actual measurements of structures that didn't yet exist. Once anchor bars were positioned and secured to bedrock using iron brackets and clamps that prevented any movement, the filling process began. Masonry, consisting of granite blocks and Rosendale cement mortar, was laid course by course, gradually filling the excavated chambers, while embedding the anchor bars in stone that would grip them with crushing force when the mortar cured and the entire mass became unified stone and metal. The interior chambers of the anchorages were designed with vaulted ceilings and arched passages that distributed loads efficiently, while creating spaces that could be inspected in future years, without requiring excavation of the surrounding masonry. These accessibility features reflected forward-thinking engineering that recognized bridges required maintenance and occasional inspection of critical components that would otherwise remain hidden and inaccessible. As masonry work proceeded upward from bedrock, level toward ground surface, workers created increasingly complex stone patterns that transitioned from purely structural work in the depths to architecturally refined masonry near the surface, where the anchorages would be visible to anyone passing nearby. The visible portions featured carefully dressed granite blocks, laid in patterns that created visual interest, while demonstrating the quality of workmanship that characterized every aspect of bridge construction. By 1876, as cable spinning was about to begin, all 4 anchorages stood complete above ground level, appearing as massive rectangular stone buildings that seemed to serve no obvious purpose beyond providing platforms where the suspension cables would eventually terminate. Yet beneath these visible structures, tons of iron and thousands of cubic yards of masonry gripped bedrock with force sufficient to resist any pull the cables might generate. The connection between the main suspension cables and the anchorage anchor systems required careful engineering to manage the transition from flexible steel cable to rigid iron bars embedded in immovable masonry. At the top of each anchorage, the four main cables arrived from the river span and divided into their component 19 strands, with each strand separating into individual wires that would be threaded through the anchor plates and secured with iron wedges and clamps. This fan-shaped spreading of cable strands transformed the concentrated load carried by each main cable into distributed forces across multiple anchor bars, preventing stress concentrations that might damage either the cables or the anchor system. The geometry of this strand distribution required precise calculation to ensure that load sharing remained equal across all anchor points, preventing some bars from being overloaded while others carried less than their design capacity. Temperature compensation represented another critical aspect of anchorage design, as the steel cables would expand and contract with temperature changes by amounts that could total several feet across the bridge's full length. The anchorage systems needed to accommodate these movements without allowing cables to slip or shift in ways that might compromise the careful load distribution that had been engineered into the anchor connections. Adjustment mechanisms built into the anchor systems allowed workers to fine-tune cable tensions after installation, compensating for any errors in initial setup or changes that might occur as the cables settled under load and the bridge structure stabilized. These adjustments used threaded components and hydraulic jacks that could apply forces measured in tons, allowing precise control of cable geometry and tension distribution. The completed anchorages, though largely hidden from public view, represented some of the most over-engineered components in the entire bridge structure. The safety factors built into their design meant they could resist forces several times greater than the cables could ever generate, providing absolute certainty that the bridge would never fail due to anchorage problems even under the most extreme loading conditions imaginable. Modern engineers examining the Brooklyn Bridge anchorages continue to marvel at the scale and thoroughness of 19th century design that created resistance systems so robust they remain essentially unchanged after nearly a century and a half of continuous service. The iron anchor bars show no signs of fatigue or deterioration, while the masonry remains as solid as the day it was installed, proving that proper engineering combined with quality materials and workmanship can create structures that approach geological permanence. The psychological impact of these anchorages extended beyond their technical function, as their massive presence announced to anyone observing the construction that this bridge was being built to last for ages rather than decades. The anchorages communicated commitment to permanence that helped overcome public skepticism about suspension bridge technology, demonstrating through sheer mass and obvious strength that the engineers had anticipated every possible failure mode and designed solutions that eliminated any reasonable doubt about long-term reliability. With the massive cables secured firmly to earth and stone, hanging in their graceful curves between towers, like steel spiderwebs, waiting to support something substantial, the bridge project entered its final construction phase, creating the roadway that would transform these separated structural elements into a unified crossing where carriages, pedestrians, and eventually the rushing crowds of a growing metropolis would flow between two cities that were already beginning to think of themselves as one. The roadway construction that began in earnest during 1878 required engineering approaches fundamentally different from everything that had come before, as workers faced the challenge of building a suspended structure that would flex and move with wind and traffic loads while maintaining the stability and rigidity necessary for safe passage. This was not conventional construction. where foundations remained fixed and structures grew upward from solid ground. This was architecture suspended in air, dependent entirely on the steel cables above for support. The first step in roadway construction involved hanging the vertical suspender cables that would connect the main suspension cables to the roadway structure below. These suspender cables, spaced at regular intervals along the entire bridge length, would carry the roadway's weight upward to the main cables, distributing loads evenly across the suspension system, while creating the connection points where roadway framing could be attached. Each suspender cable consisted of multiple steel wire strands wrapped together and terminated at both ends with forged iron fittings that provided secure connections to the main cables above and the roadway structure below. The spacing and tensioning of these suspenders required careful calculation to ensure even load distribution, as any imbalance would create uneven stresses in the main cables and potentially cause the roadway to hang at incorrect angles or elevations. Installing 1,520 suspender cables across the bridge's full length demanded coordination between workers stationed at multiple elevations, with crews working on platforms suspended from the main cables, while other teams operated on temporary falsework structures built up from boats floating in the river below. Communication between these separated work groups relied on flag signals and shouted commands that had to overcome the distance and noise that made normal conversation impossible. The roadway structure itself consisted of steel trusses running longitudinally along the bridge length, creating parallel beams that would support the actual deck surface where traffic would travel. These trusses were built up from individual steel members, connected by riveted joints, forming geometric patterns that distributed loads efficiently, while maintaining relatively light weight that minimized the burden on the suspension cables above. Steel fabrication for the roadway trusses occurred in workshops scattered across New Jersey and Pennsylvania, with each piece manufactured according to detailed drawings that specified exact dimensions and connection details. The pieces arrived at the construction site by barge and railroad, then were lifted into position using steam-powered hoisting equipment operated by workers who understood that any dropped component could fall into the river and require expensive replacement. Assembly of the truss members into complete roadway sections proceeded systematically from both ends of the bridge toward the center, with workers using temporary supports to hold partially completed sections in proper positions until enough structure existed to become self-supporting. This incremental construction approach allowed the roadway to grow gradually outward from the towers, with each new section adding strength and stability to what had already been built. Riveting the steel connections required teams of specialized workers, whose coordinated efforts created the permanent joints that held the truss members together. One worker heated rivets in a portable forge until they glowed red hot, then tossed them to a catcher, who used tongs to grab the flying rivet and insert it through aligned holes in the steel members being joined. A third worker with a heavy hammer drove the rivet head, while a fourth worker held a backing bar against the opposite side, creating the upset head that would lock the joint permanently when the metal cooled and contracted. The rhythm of riveting work created a distinctive percussion that echoed across the construction site as dozens of teams worked simultaneously on different sections of the roadway structure. The sound of hammers striking hot metal, combined with the shouts of workers coordinating their activities, created an industrial symphony that announced to all of New York that the bridge was approaching completion. The elevated pedestrian promenade, one of the bridge's most distinctive features, occupied the center of the roadway at a level 18 feet above the vehicle traffic lanes. This separation of pedestrians from wheeled traffic represented innovative thinking about urban transportation, creating a peaceful pathway where walkers could enjoy views of the harbor and city skyline without competing for space with carriages and wagons, whose iron-shod wheels and horses' hooves created noise and hazards that made street-level walking unpleasant. Construction of this elevated walkway required additional structural members that supported a secondary deck above the main roadway level, creating a double-deck arrangement that maximized the bridge's capacity, while maintaining the architectural elegance that had characterized the entire project. The promenade's width of 15 feet provided adequate space for pedestrians to pass comfortably in both directions, while stopping occasionally to admire views that would make the Brooklyn Bridge as famous for its scenic qualities as for its engineering achievements. The roadway deck surface consisted of yellow pine planking laid transversely across the steel truss members, creating a wooden surface that provided some flexibility and noise absorption, while remaining durable enough for heavy traffic loads. The pine boards, each cut to precise dimensions and treated with preservatives to resist rot and weather damage, were fastened to the steel structure, using bolts and clamps that allowed individual boards to be replaced when wear or damage eventually required maintenance. Approach ramps connecting the suspended span to city streets on both shores required extensive construction that extended the bridge project far beyond the river itself. These approaches had to climb gradually from street level to the elevation necessary for connecting to the suspended roadway, creating long ramps that consumed valuable urban real estate, while providing the gentle grades necessary for horse-drawn vehicles to navigate comfortably. The Brooklyn approach extended nearly half a mile inland from the river, passing over existing streets on elevated structures that allowed traffic to continue flowing beneath the bridge, while providing the elevation gain necessary for reaching the suspended span. This approach structure created a covered arcade beneath the roadway, where shops and businesses could operate in spaces that would otherwise serve no purpose, generating rental income that helped offset the bridge's construction costs. Gas lighting systems installed throughout the roadway length would eventually illuminate the crossing for nighttime traffic, using cast iron lamp posts positioned at regular intervals along both sides of the vehicle lanes and the pedestrian promenade. These lamps, connected to gas mains that ran along the bridge structure, would transform the bridge into a ribbon of light visible across the harbor, a beacon announcing New York's arrival as a modern city whose infrastructure could function around the clock, regardless of natural darkness. Safety railings along both edges of the roadway and the pedestrian promenade provided protection against the dangers of accidental falls from heights that could prove fatal. These railings, constructed from wrought iron, formed into decorative patterns that combined safety function with aesthetic appeal, created visual boundaries that helped prevent vertigo while maintaining open views of the water and skyline beyond. By the spring of 1883, as workers installed the final deck boards and completed the last details of railing and lighting installation, the Brooklyn Bridge approached completion after 14 years of construction that had tested every assumption about what engineering could accomplish. The roadway stretched 5,989 feet from anchorage to anchorage, creating a crossing that would transform travel between Brooklyn and Manhattan from uncertain ferry journeys into reliable passage across a structure that seemed destined to last forever. The final preparations arrived with the soft warmth of spring in 1883, as workers tightened the last bolts, swept away construction debris, and stood back to observe what 14 years of labor had created across the East River. The roadway lay complete from shore to shore. The cables hung steady overhead. The towers stood unwavering against the sky. And on May 24, 1883, the Brooklyn Bridge opened to the public with ceremonies that drew crowds unlike anything New York had witnessed before. President Chester A. Arthur arrived to walk across the span alongside New York Governor Grover Cleveland, their formal procession marking official recognition that this structure represented something beyond ordinary civic achievement. But before any official stepped onto the wooden planking, before any speech proclaimed the engineering triumph, one person had already made the ceremonial first crossing that honored the untraditional path this project had followed. Emily Warren Roebling, carrying a rooster as a symbol of victory, rode in a carriage across the bridge she had helped complete. Through 11 years of tireless work, that conventional society had never imagined a woman could perform. The opening day ceremonies began in the morning with gatherings on both shores, Brooklyn residents assembling near the anchorage that had transformed their waterfront, Manhattan citizens crowding the approach that extended inland from the tower foundations. Flags hung from buildings throughout both cities, banners stretched across streets, businesses closed to allow workers to witness the occasion. And by noon, an estimated 150,000 people had gathered near the bridge or positioned themselves at vantage points throughout Lower Manhattan and Brooklyn Heights, where they could observe the historic opening. The formal procession began on the New York side, with President Arthur and Governor Cleveland leading a delegation of officials, engineers, and dignitaries, who walked slowly across the 5,989-foot span, while crowds pressed against the barriers that kept the pedestrian promways clear for the ceremony. Emily Roebling rode near the front of this procession, her presence acknowledged by those who understood that without her mathematical knowledge, her administrative coordination, and her unwavering dedication during the years when her husband Washington could not leave his sick room, the bridge might never have reached completion. Washington Roebling watched the opening ceremonies from the window of his Brooklyn Heights residence, his health too compromised by caisson disease to allow him to join the crowds crossing the structure he had supervised through construction's most challenging phases. Through a telescope, he observed the procession moving across the bridge, saw the flags waving in the May breeze, watched the crowds celebrating the completion of work that had consumed his life since 1869, when his father John had first begun construction before dying from tetanus just weeks into the project. From that window, Washington witnessed the realization of his father's vision, the dream of a permanent crossing that would unite two great cities through engineering that pushed beyond every established limit. The scene unfolding before him represented 14 years of constant problem-solving. The caisson work that had nearly killed dozens of men, including himself. The foundation excavations that reached depths no one had attempted before. The material challenges that required sourcing limestone from quarries and steel from mills across multiple states. The cable spinning that created the strongest suspension system ever constructed. The tower masonry that rose 276 feet above the water to support unprecedented loads. The evening brought fireworks displays that lit the night sky above the East River. Rockets bursting in colors that reflected off the water and illuminated the bridge's twin towers and graceful cables. Ships in the harbor sounded their horns in celebration. Church bells rang throughout Brooklyn and Manhattan, and people continued crossing the bridge long after sunset, walking slowly along the elevated pedestrian promenade 18 feet above the roadway, pausing to look down at the water flowing beneath them, marveling at the steady feel of the structure that showed no movement despite the thousands of people traversing its length. The gas lamps along the promenade created a gentle glow that guided walkers across the span, their light soft against the darker sky, their steady flame a symbol of the permanence that characterized everything about this bridge's construction. Families walked together across the East River for the first time without boarding a ferry. Children pressed against the railings to watch the water below. Couples paused mid-span to take in views that stretched from the harbor to the city lights spreading inland from both shores. The cost of this achievement had measured far beyond the $15.5 million spent over 14 years of construction, a sum that represented enormous public investment in infrastructure, but that could never account for the human price paid during the bridge's creation. 27 workers had died during construction, men who fell from towers during masonry placement, laborers who perished from caisson disease in the compressed air chambers beneath the river, riggers who lost their grip while working hundreds of feet above the water, craftsmen who suffered accidents during the countless dangerous tasks that building this bridge required. Their names appeared in construction records and newspaper accounts. Brief mentions of lives lost in service of this crossing. Families left without fathers or brothers or sons. Widows facing uncertain futures after accidents that occurred in pursuit of wages that might support a household. The opening day speeches acknowledged these deaths with somber recognition that progress sometimes demanded sacrifice. But the ceremony's triumphant tone suggested that most observers preferred celebrating the bridge's completion rather than dwelling on the cost that had made it possible. Emily Roebling's role in the bridge's completion received acknowledgement during the ceremonies. Though 19th century conventions prevented the kind of recognition that a male chief engineer would have received for equivalent contributions, newspaper accounts described her as the lady who supervised construction, or Washington Roebling's capable assistant, language that diminished 11 years of work, that had included mastering complex engineering calculations, coordinating material deliveries, communicating technical specifications to contractors, resolving disputes between workers and supervisors, and maintaining project momentum during periods when questions arose about whether construction should continue under such unusual management circumstances. She had learned strength of materials analysis, structural mechanics, cable engineering, and bridge construction methods, not through formal education that universities denied to women, but through private study and practical application that transformed her into one of the era's most knowledgeable bridge engineers. Despite holding no official title and receiving no formal credit for her contributions, the bridge's immediate impact on travel between Brooklyn and Manhattan exceeded even optimistic predictions. Within weeks of opening, thousands of people crossed daily on foot, by horse-drawn vehicle, and soon by electric trolley that made the journey faster than any ferry had managed. The elevated pedestrian promenade became a favorite destination for evening walks, its height above the roadway traffic providing quiet space where people could stroll while enjoying river breezes and city views without competing with vehicles below. Artists set up easels along the walkway to paint harbor scenes. Photographers captured images of the towers and cables that appeared in newspapers and magazines throughout America and Europe. Tourists added the bridge to their New York itineraries, recognizing that this structure represented achievement worthy of traveling to witness. The Brooklyn real estate market boomed as the reliable crossing made commuting to Manhattan practical for middle-class families who could afford larger homes in Brooklyn than Manhattan's crowded neighborhoods offered. The bridge's influence extended beyond transportation improvements. Its completion demonstrated that American engineering could match or exceed European achievements that had previously set standards for ambitious construction. The Brooklyn Bridge became proof that the United States possessed the technical knowledge, the industrial capacity, the skilled workforce, and the civic will to undertake projects of genuine grandeur, structures that served practical purposes, while also creating beauty that inspired observers and challenged assumptions about what engineering could accomplish. European engineers who had dismissed American capabilities as limited to utilitarian projects now studied the Brooklyn Bridge's innovative design, its pneumatic caisson foundations, its steel cable system, its unprecedented span length, its integration of function and aesthetics into unified design that worked as both transportation infrastructure and architectural monument. The decades following 1883 brought continuous use that validated every aspect of the bridge's engineering. The foundations remained stable beneath the river. The towers stood firm against wind and weather. The cables supported growing loads as traffic increased. The roadway accommodated changing transportation technologies from horse-drawn carriages to automobiles, to modern vehicles carrying weights that 1880s designers could hardly imagine. Maintenance workers repainted steel components, replaced worn deck boards, updated lighting systems from gas to electric, added traffic lanes as usage patterns evolved. But the basic structure remained unchanged, its fundamental soundness requiring adjustment rather than reconstruction. By the time Brooklyn and Manhattan merged into Greater New York City in 1898, the bridge had already become so integral to daily life that residents could barely remember when the East River had presented a genuine barrier requiring ferry service for every crossing. More than 140 years after its May 1883 opening, the Brooklyn Bridge continues carrying traffic across the East River, its granite towers still rising above the water, its steel cables still supporting the roadway deck, its pedestrian promenades still welcoming walkers, who pause mid-span to observe harbor views and city skylines that have transformed completely, while the bridge itself remains fundamentally unchanged. The structure has witnessed the entire modern history of New York City, the rise of skyscrapers that dwarfed its towers, the evolution of transportation from horse-drawn vehicles to automobiles, to the constant flow of contemporary traffic, the growth of Brooklyn and Manhattan into the dense urban landscape that defines modern New York. Through all these changes, the bridge has endured, not as a museum piece preserved from active use, but as functioning infrastructure that serves the same essential purpose its builders intended, connecting communities that have grown and changed, while the crossing that links them continues performing the role that John Roebling envisioned, that Washington Roebling supervised through construction's most challenging phases, and that Emily Roebling helped complete through dedication, that overcame every obstacle society placed in her path. The Brooklyn Bridge stands tonight as it stood on opening day in 1883, steady, strong, beautiful, a permanent crossing that turned an impossible dream into stone and steel reality that endures as testament to what human ingenuity can accomplish when vision, determination, and skill combine to create something meant to last forever. The Brooklyn Bridge rests tonight as it has rested for more than 140 years, its granite towers standing steady against the darkness, its steel cables forming graceful curves that catch the glow of city lights, its roadway stretching across the East River in a span that once seemed impossible, but now feels permanent as the water flowing beneath. The sounds of traffic crossing between Brooklyn and Manhattan blend with the soft movement of night air around the cables, a quiet rhythm that continues hour after hour, year after year, decade after decade, while the bridge holds its position between two shores that have grown and changed beyond recognition since 1883, when crowds first walked across wooden planking that smelled of fresh pine and new paint. The workers who built this bridge have long since passed into history. The men who descended into caisson chambers beneath the river, the masons who placed each stone in the towers, the riggers who spun steel wire into massive cables, the carpenters who installed deck boards and railings, the engineers who solved problems no one had encountered before. Their names appear in construction records and old newspaper accounts, brief mentions that hint at lives devoted to wages, earned through dangerous work that required strength, skill, and courage that modern observers can only imagine. Some of those workers never left the bridge, their lives ending in construction accidents that took 27 men during 14 years of building. Their contributions measured not just in labor performed, but in the ultimate sacrifice that sometimes comes when humans attempt to create structures at the very edge of what engineering knowledge permits. John Roebling never saw his bridge extend beyond the initial foundation work. His death in 1869 from tetanus infection, ending a lifetime of bridge design just weeks after construction began. Washington Roebling spent 11 years confined to his sick room, his body damaged by caisson disease, but his mind remaining sharp enough to supervise construction through written instructions and observations, made through a telescope aimed at the bridge site visible from his Brooklyn Heights window. Emily Roebling transformed from a young woman with no engineering training into the person who carried her father-in-law's vision and her husband's determination across the finish line, mastering technical knowledge that universities refuse to teach women, coordinating construction that conventional society insisted women could not manage, proving through 11 years of steady work that capability matters more than the prejudices that try to limit what certain people can accomplish. The bridge remembers all of them, not through conscious memory, but through the permanence of what they created together. Every stone in the towers represents decisions made about materials and methods. Limestone blocks hauled from quarries, granite facing shaped by skilled masons, mortar mixed to specifications that ensured strength across generations. Every wire in the cables carries forward the innovation of engineers who understood that steel could be drawn into strands strong enough to support unprecedented loads. 5,434 wires per cable, 4 cables total, each one spun by workers who traveled back and forth across the river hundreds of times, building strength through patient accumulation of individual elements that gained power only when combined into unified whole. Every timber in the anchorages, every bolt in the roadway framework, every rivet connecting steel components, all these pieces remain in service, still performing the functions their builders intended, still bearing loads, still holding steady against wind and weather and time. The East River flows beneath the bridge tonight as it flowed during construction, its tides rising and falling with the same rhythm that complicated caisson work in the 1870s, its currents moving with the same force that ferry captains navigated before 1883, its waters reflecting city lights that have replaced the gas lamps and oil lanterns that illuminated the harbor during the decades when this river represented a genuine barrier between communities that could see each other across the water but couldn't easily connect. The river remembers when crossing required boarding a ferry, when fog delayed service, when ice stopped boats completely, when every journey between Brooklyn and Manhattan involved uncertainty and waiting and acceptance that the water controlled travel between the two cities. Now the bridge provides passage that ignores weather and tide, a crossing available every hour of every day, reliable as sunrise, steady as the granite foundations hidden beneath the river. The cities on both shores have transformed beyond recognition since opening day. Skyscrapers rising to heights that make the bridge towers seem modest by comparison. Populations growing from hundreds of thousands to millions. Technologies evolving from gaslighting and horse-drawn vehicles to electric systems and automobile traffic, and all the complexity of modern urban life. Brooklyn and Manhattan merged into Greater New York in 1898. The separate cities that built the bridge becoming boroughs of a metropolis that now depends on dozens of bridges and tunnels connecting its parts. But the Brooklyn Bridge remains special among all these crossings, not because it carries the most traffic or spans the longest distance or represents the newest engineering techniques, but because it came first, because it proved the impossible could become real, because it stands as beautiful as it stands functional. A structure that serves practical purposes, while also inspiring the kind of admiration usually reserved for art rather than infrastructure. Tonight the bridge waits in darkness softened by lights, ready for tomorrow's traffic that will cross between Brooklyn and Manhattan as traffic has crossed for more than 140 years, ready for walkers who will traverse the elevated pedestrian promenade as countless others have before them, ready to continue performing its function without complaint or expectation of recognition beyond the simple fact of endurance. The bridge asks nothing except to be allowed to stand, to hold its position between two shores, to support the loads that cross its span, to remain what its builders intended, a permanent connection that transformed uncertainty into reliability, that changed impossible into inevitable, that proved human ingenuity could create structures worthy of lasting forever. As sleep approaches, imagine the Brooklyn Bridge resting beneath the night sky, its towers rising towards stars that watched construction progress year after year, its cables forming curves that follow the mathematical precision of catenary arcs, its roadway stretching across water that flows eternal and unchanged despite all the transformation happening on the shores it separates. The bridge stands steady, neither boasting of its accomplishments nor lamenting its age, simply existing as what it has always been: stone and steel, shaped by human hands into form that serves human needs while creating beauty that transcends utility. 14 years of construction created something meant to last for centuries. And tonight, more than 140 years after opening day, the Brooklyn Bridge continues fulfilling that promise. Rest now. Let the image of the bridge carry you towards sleep, its steady presence a reminder that some things endure, that careful work creates lasting value. That vision combined with determination can accomplish what seems impossible until the moment it becomes real. The Brooklyn Bridge will stand through this night as it has stood through countless nights before. Patient, permanent, peaceful, a crossing that connects not just two cities, but past and present and future, all joined by granite and steel, and the human desire to build something beautiful that lasts forever. The bridge sleeps beneath the stars, and so can you, knowing that when morning comes, the Brooklyn Bridge will still be there, still serving, still standing, still proving that what we create with care and skill and dedication can outlive us all and continue blessing generations. We will never meet with the gift of crossing between shores that once seemed forever separate, but now, thanks to this bridge, remain forever joined. Sleep well. The bridge watches over the river, steady and strong, eternal and unchanging, a permanent testament to what human hands can build when guided by vision that sees beyond the limitations of the present moment toward a future where the impossible becomes simply real.